Hi, everyone. I am Dave Aronczyk. I'm a product manager at Google, and I'm one of the co-founders of the Kubeflow project. And we are here to talk. This is Matt in the front row. You'll be seeing him in a minute. And we are here to talk about open source Kubeflow and TensorFlow running on top of OpenShift. A really new paradigm in the world of machine learning. A lot of people are kind of curious. You know, anytime you see TensorFlow, anytime you see machine learning, you're like, I got to find out what this is. And they approach the problem, and they don't really know how to understand how it impacts their business. And I think a lot of the reason is from this. You know, everyone has a different idea about what machine learning is. So we're going to spend a few minutes here just getting everyone up to speed. First, you start with a question. Not hard. For example, you might say, how much is my house worth? That is a very easy question to ask. From that, then you say, OK, well, what data do I have? I know what answer I want to get. I want to know how much my house is worth. What data do I have? Maybe I'm going to use square footage. It's a pretty good metric. Larger houses generally go for more. And then you start to collect data around it. For example, you got a point. Points usually not enough. You usually need more points. Anyone want to try and draw the line here? You're kind of cheating because you know there's the corner there, right? So then you get more points, and then you get even more points, and then you draw a line. And then you're like, aha, I have an answer. Because now I can answer my question, right? I say, my house is 2,100 square feet, therefore $339,000. Not in San Francisco, of course, you know, but most places. Congrats, you're a machine learning expert, really. So certificates on the way out. But things can get complicated. You could have nonlinear groupings. You could have multidimensional. We only had one dimension there. Maybe you have many, many dimensions. Things could change over time, which is obviously very complicated. And what I think this all goes to is that machine learning, you know, while it captures a very simple concept, taking a bunch of data and making a regression out of it or using some standard techniques, at the end of the day, what we believe is that machine learning is a way to get at that answer for your business problem without explicitly knowing how to create the solution. And generally speaking, it's great. People love it. At Google, this is what machine learning did for us. You took the best data center engineers in the world who have dedicated their life to using renewables, using latest technology around data center energy usage, trying to figure out how to make the most out of every watt that goes in machine learning, or excuse me, in data center terms, this is called power usage effectiveness. The amount of power that goes in, how many cycles are you able to get? Before machine learning, they did everything they possibly could to figure out what the hell was going on and tune it to the nth degree. They attached machine learning to it, and they got a 40% reduction in overall usage. I mean, this is literally hundreds of millions of dollars a year. And this is better than anything that they had done or even thought of before. And the first thing they did, they wanted to understand what the hell was going on, which is often impossible because nobody really knows what machine learning is doing. But they were able to tease it apart, and it took it in new directions and things like that they hadn't even thought of. And again, it goes back to this point. Machine learning is a way to get at that solution, lowering energy cost, without having to think about exactly what the right way is to do it in the first place. However, machine learning is very hard. And it's not just because I'm terrible at math. It is because there's this gap. The gap is that everyone sees this magical AI goodness, hundreds of millions of dollars, much more in savings, much more efficient data centers, much more efficient businesses. But most folks are on the way other end of the spectrum. And in between, there's a lot of pain. And the pain generally comes from a bunch of different things. But most of all, it comes from having to wire together this insanely bespoke solution that is custom for every single deployment you roll out, every single library, every single news model. You have to retrain and redo everything. And this is not ideal, right? You know, this is kind of like software was in, 1965, before people had invented C and common languages and common ways to share code. And the question is, haven't we heard this before? And we actually heard this really recently. Before I started on Kubeflow, I was working on Kubernetes. And Kubernetes, came along in 2014, and people were doing the exact same thing. They were running custom orchestrators, they were running custom service discovery, they were wiring everything together, they were using cron and bash, OpenShift, I'm looking at you. But the reality is they were doing all this stuff because no one had come along and developed a common set of APIs. And the reality is that OpenShift and Kubernetes really did make huge progress against this overall orchestration system when they launched to give people a common set of APIs and a common way of rolling out these platforms in packaged ways where all the dependencies and service discoveries and the ugly stuff was kind of taken care of for you. And the way that they did, what this enabled was true extensibility. At KubeCon, about 6 months ago, Ken Goldberg, engineering director for the Kubernetes project at Google, came on stage and talked about the extensibility of Kubernetes. And this is a really key point. You know, what Kubernetes provided was this common set of APIs, but it also provided common extension points for people to build on top of it, so that you could use all the native elements of Kubernetes and trust that it was there. As long as you were running on a Kubernetes conformant cluster, you could be assured that there would be DNS, that there would be a way to mount storage, that there'd be all these various things. And this is extremely important because it enabled what are called cloud-native apps. These are apps that are designed to run in these distributed systems. They're loosely coupled together, and they allow you to swap in and out all the various components that are involved in rolling out a modern application. So I would propose that we need cloud-native ML. We need ML that understands that it doesn't have to go all the way down to that nth level of depth. It's able to use a standard set of APIs and then build all the elements on top of it. And what this looks like for us, it really breaks down to these three key components: composability, portability, and scalability. For composability, what I mean is the following. Lots of people out there will focus on the building of your model. And that's great. Obviously, that's very, very important. But if you go and talk to a data scientist, building a model is a very small component of what you have to do. It's all the things around it that can be very, very painful. Ingesting your data, transforming it, splitting it, running through initial experimentation, finally getting to building your model and validating it, then training it at scale, and finally rolling it out to production. That's what a real solution is. If you want to get the answer to your house, you have to do all of these things. Or the answer to how much your house is worth, you have to do all of these things. There's no easy shortcut to just say, well, I just want to focus on the model. Now, the problem is that rolling out all these services is critical, but every data scientist is also going to have a slightly different take on it. They say, well, I don't want to use Hadoop, I want to use Spark, or I don't want to use TensorFlow, I want to use PyTorch, so on and so forth. These are all components that a data scientist is going to be familiar with, and we want to help enable that. So that's part of the part of composability. The second is portability. Setting up all those things often is an enormous job, but that's kind of even half of the problem. Then you have to think about all the things underneath it: runtimes, drivers, OSs. These are all components that you need to think about as well. What version you're running on, and how you get your drivers installed, whether or not one version of a hardware works or doesn't. These are additional components that you need to worry about. And so you could spend a whole bunch of time setting that up, and then you have to replicate the exact same effort when you get to training, because your cluster may be very different, or when you get to the cloud, because your cluster may be further different again. And then anytime something changes, NVIDIA releases a new driver, you have to go back and re-update all these deployments again in a very complicated way. Again, not ideal. Folks are really looking for portability, a way to describe your overall framework in a way that can be stamped out everywhere. And then finally, scalability. Obviously, Kubernetes scales to thousands of nodes, and that's great. And you can spin up very, very large deployments of VMs, right? And they're now single clicks away in your cloud. But that's not really the only thing when it comes to scalability. Obviously, then you have to think about accelerators, whether or not you're using GPUs, you're using custom cloud accelerators like Google's TPUs or Microsoft's FPGAs that they just announced, a variety of different CPUs. Are they single core? Are they multi-core? Different disk? And then there's also the human being aspect of scalability. How do you scale humans? Are they different skill sets? Intern to 20-year-long researcher, data scientist, SWE, different engineers. How do you scale your teams? literally grow a single team or add additional teams, potentially geolocated. And finally, more experiments. So even if everything else stays the same, maybe you just want to run 5, 10, 100 different experiments simultaneously to see what one works best. Those are all different elements of scale. But at the end of the day, it comes back to those 3 core components for what we mean by cloud-native ML. And the way we decided to help make progress against this and build this is by relying on something that is already great at composability, portability, and scalability, and that's containers, Kubernetes, and obviously OpenShift as well. Except, if you want to use ML on Kubernetes, you end up having to become an expert in a lot of things, and that's not great. Especially if you're a data scientist who wants to operate at that level where you're trying to decide, what model works great, or how you're going to do your data transform, or whether or not you A/B it out in production. Having to think about service endpoints and persistent volumes and scaling, immutable deployments, all these elements, not ideal. So to solve that problem, excuse me. Oops, shoot. Sorry. To solve that problem, we introduced Kubeflow. And the idea behind Kubeflow is, excuse me. The idea behind Kubeflow is we want to make ML easy for everyone to develop, deploy, and manage portable, distributed ML on Kubernetes. And what that looks like is the following. First, we introduce that bottom layer, or we don't even introduce it. We just rely on the fact that it exists. Kubernetes, OpenShift, they run anywhere. They run on any cloud, they run on premises, they run on your laptop. They're already there, and they provide a great layer of abstraction with a core set of key APIs that are available. So you can rely that they work properly. Second, you describe your deployment using Kubeflow and Kubeflow native packaging. We're not introducing anything new. These are all open source projects. But we rely on the fact that you can containerize everything and you can describe it in code. And then you're able to just stamp it out. Every place that Kubernetes exists, Kubeflow runs fine. And specifically, as of last Friday, we are introducing Kubeflow 0.1. The project initially kicked off at KubeCon Austin about 6 months ago, and we're at the 0.1 release. In the box right now, we have a Jupyter Notebook. We have distributed multi-architecture training. We support different model serving frameworks. And we have KSNet packaging such that you can build it and roll it out yourself in any customization you'd like. And I wanted to really stress on that. Even though TensorFlow is in the box right now, we really do want to support every single model framework that's out there. We already have PyTorch and Caffe checked in as operators, and they're just going through the final process to get that rolled out. We want to support every different data transform. We want to support different IDEs for engagement, serving frameworks, all those various things. We're just getting started with what we know, but we're going to be very excited to roll out quickly. And with that, let me hand off to show you this thing live and running.
Great, thanks, Dave. So hopefully everybody's awake and has their bingo cards out. This is the live demo part, so get ready for the carnage. This is, I'm gonna have my fingers crossed on a new network here and whatnot. Before we get to the actual demo, I want to give you a little bit of an idea of what you're going to see, what you're going to watch me build here. And this is it. It's really exciting, isn't it? When you go and you build your first programming application, it's hello world, pretty simple, but when you actually get it done, it's amazing. This is essentially the hello world for machine learning. It's handwritten character recognition using the MNIST data set. And if you're really quick with your phone at the end, you'll actually see an endpoint that I expose live that you can copy and play around with this if you want yourself, at least until I turn it off. So there are basically four steps that we have to go through for building an application using machine learning. The first, Dave talked about already, where he talked about having Jupyter notebooks so that you can actually process your data, construct the model, tweak it, tune it, do everything locally so you can get a good feeling for if things are going to work or not. Once you have that, you take the code, you stick it in a container, and you run training experiments on it. You do hyperparameter tuning to figure out what's the best configuration for the model that you can produce that will then get pushed into your application. Once that's built up, you can actually do the serving. This is where you take the trained model, you deploy it, you put an API in front of it, and then you can connect your business logic, your application logic to it, which is the fourth step. So now for real to the demo. So hopefully folks can see this mostly in the back. When I was putting this together, I realized that it has some of the great things that you like in a demo. It's got, I think, 11 different concepts that you're going to get to smash into your head, but you came to this session, so you're all really smart, and it shouldn't be too much of a problem. The first few are obviously OpenShift and Kubernetes, which you're probably very familiar with already, and public and private clouds are the second two. So that's 4 right there. The private cloud is going to be my laptop. The public cloud is a cluster running in Google Cloud. So on the left here, we actually have OpenShift running on my laptop. On the right here, we have Kubernetes running on Google Cloud. So what I'm going to do is start off by just taking Kubeflow, downloading it, and deploying it on both of our clouds. So the first thing we have to do here is actually start a new project, a case on it project, which is a tool for essentially programmatically defining the JSON objects that you're going to push to your Kubernetes API. And this is done in a way that you have no syntax problems. You don't have to worry about kind of like niggly things about where the commas are, extra, whatever. You can really just think about the environment that you're working in and push to. So starting this up, once I've got the project created here, I want to do 2 things. I want to tell it about both of the clouds that I have. So I'll do that. I'm going to create an environment that's saying there's a cloud. This is the thing on the right. And an environment that's just going to be the local connection I have here. So there we are. Got 3 environments, gave me 1 default for fun. So after that, I can just basically install, download Kubeflow. So this is all you have to do. It's going to be registering connection to GitHub, where we store all of the packaging objects, pulling down the core pieces, which include things like TensorFlow, and then also the operators for doing your training, the TF job, as well as serving. So that's all there now. So that's great. Next step is to generate an example of kind of the core components that will push out to both of our clouds. And that's done. This is going a little fast. Hopefully it's not too fast. Once that's done, we can really just push that configuration to our Kubernetes deployments. So this one's pushing over to the OpenShift. You see all the objects popping up there. And this is really key. We can do this exact same thing. I'll do this really slowly. The exact same commands, the exact same configuration, but we'll do it over to Google Cloud. See the objects coming up there at some point. Anyway, so while those are coming up, I want to point out or bring you to the first piece of building this application, which is actually trying to build the model itself. So over here, I'm just going to do this locally, as you probably would. We've got this TensorFlow hub. It's actually Jupyter Hub. So this is basically the kind of like the magical endpoints to connect to all things Jupyter, which lots of the data scientists in the room, or if you work with data scientists, are really familiar with that, and even more developers are getting familiar with it in addition to the other IDEs that they use. So I'll just expose an endpoint to this so I can actually connect to the Jupyter Hub, and boom, I've got access. Can log in, say I want to create my own Jupyter Hub. We package in a number of different notebooks that you can use, specify if you have GPUs on your cluster or not. I'm not actually going to spin this up because I'm connected through my phone hotspot, and I don't want to burn all the data for this month. So instead, I'm just going to give you an example of the actual TensorFlow Jupyter notebook that we put together. Some really smart data scientists at Red Hat put this together for me. And this is all the TensorFlow code that's needed to do the training, to build up a model, to do the character recognition. So from here, once we actually have this code, we want to have some way of doing repeated experiments, repeated training of this. So we really take it from here, stick it into just a regular Python file, mnist here. Must hit tab. Mnist file and add like a little bit of boilerplate around it. So once the model is actually trained up, we have to save it somewhere. So we take it and we'll stick it into Google Compute Cloud, Google Cloud Storage. Okay. And to do that, basically, I have to build a container where we'll store that training code. So this will kick off. This does probably all the expected things. This is actually another concept here, container creation through Docker, but probably everybody's comfortable with that too. Should just take a moment, although my laptop's been a little finicky ever since we plugged in the clicker. But there we go. All built and all pushed. So we actually pushed this to the Google Container Registry to make sure that we have access to it both on my laptop and on the cloud, because we're going to do the training in both environments. Great. I need to make sure I know what the training version is, because when you're doing these experiments, you're actually doing tens, hundreds, thousands of them potentially. You want to be able to track them immutably, labeled across time. So, oops. So next up, we'll actually do the training. To do this, we're going to have to instantiate one of these TF job operators, which is that kind of like simple command. Now I've generated kind of the base prototype of JSON code. Next thing is to actually say what is the image that's going to be run as part of this training job. Just use that image that I had before, and because it's most helpful if I can find things later, I'm gonna give it a name as well. So now I have an instance of an experiment that I want to run. So then all it is to actually run that experiment is to say, okay, I want to take this training job and I want to deploy it on my local cluster, like that. If we go back over here to OpenShift, we can see that this CRD has been started up. The TF job operator that we had picked it up, started up a pod, and here it is actually training the model. So we can do that. One of the things that's really key here is we can do that both locally and remotely with the exact same code, the exact same configuration. So we just basically run the exact same command with one tweak, is that I'm going to point it at the Google Cloud instead here. And we see the same thing. Training job showed up. Logs are running. Runs them in reverse order, but same basic idea is going there. Okay, so now we've got code built. We've got model trained. We have to do two other things. We have to, one, start up that application that you're all going to try to get onto with your phones. And then we have to actually serve the model to the application. So our application is stored just like everything else in a container. This web UI or some Python, some Flask code in there and whatnot. I'm not going to build that container just for the interest of time. It's already deployed. So what I'll show you instead is actually just deploying that. So I'm going to push this new configuration, doing a deployed service, off to the Google Cloud. And this is going to get set up with a load balancer that you can actually access here in a second. So here's the web UI. It's up and running. Looks like the load balancer hasn't started up yet, but that's okay. While it's starting up, we'll go back and we'll deploy the model itself. So to deploy the model, we go back to using some of the Kubeflow magical packaging technology. Basically, this instead of the TF job before, this is the TF serving. We're going to call this mnis serve, which is going to give us an endpoint that the application can talk to. We're going to tell it where we stored the model in the Google Cloud, and then we're just going to deploy it. We're going to deploy it over here on the Google Cloud. So go back, we can see all of a sudden it's spinning up right here. So with that, and the application has started up, this is where you go to that IP address if you want. We tell the application, oh, here, we spun up the model for you. You can connect to it. It's on this point, this address and this port. Hopefully it's started up. But if it hasn't, sometimes it takes a moment or whatnot. But in any event, it will, and it probably is for people who are hitting it on their phone right now. So just to quick recap here, what you no, melting my laptop. Quick recap. What you saw here was essentially the ability to build the hello world for machine learning applications. This was seeing how you can uniformly deploy everything across Kubeflow, seeing how that you can use Jupyter just basically right out of the box, how you can train models, how you can build models, and then how you can serve them and connect them to your application. And with that, I'll hand things back over to Dave.
Thanks so much. So yeah.
Oh, thank you.
So yeah, it's for those that haven't done a lot of data science. When I first saw that, when I first saw the capabilities there, you're just blown away. The amount of pip installs and dependencies and various things that you normally have to do just to set that up is crazy. But we didn't use any bespoke solutions. You saw us using absolutely standard, packaged, stored in registries solutions that were designed to work together, that all you do is you describe, I want this component, this component, this component. They download, and they run, and they're well tested. You also didn't see anything specific, cloud specific. You saw deployment to your laptop, and you saw deployment to the cloud without using any specific cloud native solutions or anything like that. You just saw us use the components that were already there because Kubernetes solves this problem for you. And where we did have to make configuration changes, for example, using where you stored your model, maybe on your, you would store it on your local laptop, but then when you move to Google Cloud, you might use it on a Google storage bucket, Google Cloud storage bucket. You were able to do that via a parameter, which is appropriate. You don't want to have to go in and change code just to make a small configuration change like that. That's all. That kind of flexibility is all built into the system. And finally, you didn't see any forking of the underlying Kubernetes native APIs. This is anywhere a Kubernetes conformant cluster is running, this works. And I really do think, I like to take a minute here just to say what we are on the verge of. Data science can save lives. There's this great story out of Sweden where they were finding that women and stay-at-home parents were being injured far more after early snowfalls. And they went through and they looked at all the data they had, from hospital records to street records and accidents and things like that, and they discovered this was entirely a factor of the order in which they were plowing. They ended up plowing streets before sidewalks. And after they looked at that and they revamped it and realized they could reorder it, because cars can handle a light snow, whereas human beings can't, they were dramatically able to reduce the overall incidence of injuries. Really, really powerful stuff. And that's what we have the opportunity to do right now around data science. We have the ability to help unlock all of these capabilities for all of the people, the experts in these other fields, without having to ask them to be experts in hardware and drivers and specific models and things like that. We're working on a place where we can provide these great layering technologies and let everyone focus on the things that they do great. We are just getting started. You can see a small set of the people who are working on this right now. We have over 70 committers from 17 different companies, over 700 commits since we launched 6 months ago. We are really, really excited, but we are still very, very early. It's a 0.1. I would not recommend using it in production yet, even though there are many people doing it. That's up to them. Mostly the people on the left there that understand the code base very, very well. And I should say that all the components are not new. These are all things that have been battle tested. TensorFlow, Jupyter, TensorFlow Serving, Selden Core, Ambassador. These are well understood open source projects with very big communities. We're really working on the packaging and the wiring them together. And that's where we think there's still some work to do. And you can see some of the things that we'll be working on next. Our 0.2 release, we are targeting this summer. It will have improved setup, improved Kubernetes integration for native Kubernetes, things like auto-scaling, accelerators, and lots more packages and frameworks. But most of all, we want to hear from you. What are the things that you'd like to see? Please come join us. Please contribute. We have Slack and GitHub and open design and everything like that. If there's a proposal or something that you'd like to see as a next step for us, we'd love to hear it. And specifically, I do want to call out the machine learning SIG in the OpenShift community. They've been wonderful collaborators. Obviously, we're here on stage talking together. But we have this every 2 weeks, and it is extremely important for us to get out there, to listen, to see what you'd like to see next, and this is a great place to talk as well. You know, take down all these URLs and emails and Twitter handles. Let us know what we can do next.